So this folder that you can see is already there on the shared cloud folder that I have for you guys. So basically this GIAN CFD simulation files. So I have saved 3 subfolders over here. We are first going to start with this ICEM. Now, recall what we had briefly discussed yesterday. We first built the geometries from the CT scans, right? And some of you can come on this side because you might want to see my face. So first we start from the CT scans, and the CT scans are brought in DICOM format into a software which can segment the scans, as in pick out the correct radio density to figure out the airspace. And as I mentioned, we can do it with Slicer 3D, which is open source, which you can get here. The one that we have been using has been Mimics, which the license is kind of expensive. They might still have it here, especially if you guys have collaborations with medical schools. They prefer that because it is quite precise in the sense of how the segmentation happens. We are not going to go into the segmentation part here today. The geometries have been built and has been exported to a CAD software. For the CAD software, we are using ANSYS ICEM. You can use something else. So from Mimics, you generate the STL file, which is the geometrical structure, and you bring that STL file into a CAD software. You can use SolidWorks as well, or any other meshing tool. But along with just meshing on the CAD software, we also do the region separation. So as you saw in the work that we have been doing, I think in the second on the second day, I showed a geometry with all the sinus cavities marked out. So you can do that on ICEM in simple, or based on the question, you figure out what target sites you have to track in terms of particle deposition. So the geometry that I'm going to show today just has the nasopharynx marked out as a separate region, and the rest should be intact, the anterior airway. After the nasopharynx, there is a nasopharyngeal outlet as well. So let me first go into this folder ICEM, and I'm going to open. I have all these files saved and the mesh has been built, so I'm not going to redo everything, but basically give you a flavor of what needs to be done. So if I would encourage that you save all the folders that I have shared, and in the afternoon session you can go into the CAD lab and use these files. So I'll first open the nasal geometry, the nasal cavity geometry, which does not have the mesh. And the first thing that we are going to do today is develop the mesh file. Anyone here has used ANSYS ICEM? Okay, so this is the geometry. You can make it nicer by doing this. So on the left panel, you have the different parts that I have marked out already. So over here, as I told you, we have the nasopharynx, which is in gray. All the rest I have colored. I've given the same color, but you can right click on the parts and choose a different color. So for example, for the left airway, if I change the color to something else, this is the left airway, and this is how we do it. We distinguish between the left and the right airway, because as I have told you guys that the two sides of our nose are asymmetric. So the trends could be different on the two sides of the nose for the same person, and they are always different. Anyways, so now the idea is we have to first develop the mesh before we can run the simulations. To do that, we go to this mesh option at the top, and we need to first think about what kind of mesh we are going to build. The mesh that we use, and we have published a lot on this meshing standards. We first developed the tetrahedral mesh with a certain level of grid refinement. And once the tetrahedral mesh has been built, you can use it for simulations, but there is this caveat that eventually for the biomedical applications in this space, you are trying to get regional deposition patterns, be it for infection transmission or for drug delivery. So the mesh has to be resolved ideally near the regions where you are tracking that particle deposit. In other words, you are tracking the particle deposits along the walls. So next to the wall, the mesh has to be finely refined beyond what is there in the best tetrahedral mesh. To do that, we will do a second layer of grid resolution where we develop prismatic cells along the walls. But that is the second phase of meshing. Let's first try to get the tetrahedral mesh built. So we go to mesh, we go to this first option under there, and this step, if you end up using ICM, it would be a trial and error thing, because as you decide the scale factor, the maximum element size, the total number of mesh elements of course would change. Now the gold standard, or I would not say the gold standard, but things that we have done mesh grid refinement studies on showed us that for a geometry like this, in the sense that a geometry that is ending at the base of the nasopharynx, and this bottom red panel is red region is just that tubular outlet which we keep to make sure that the flow is still well developed and we don't have any end layer effect at the nasopharynx. So for a geometry which is basically limited at the nasopharyngeal base, we saw that 4 million tetrahedral mesh elements is sufficient. So we have to figure out the scale factors and the maximum element size and the minimum element sizes accordingly. Now, if you have a model that is further that includes the further downstream tracks, so for example the 3D printed model that I had brought, you of course need more elements. So for example, the one that some of the results that I showed during the research talk, where we had the full airway till the base of the trachea, I had around 13 million elements. No, 10 million elements in the tetrahedral mesh, and then 13 million while after I built the prism cells at the walls. So 10 million is the rough number for the tetrahedral mesh if we include the rest of the upper respiratory tract. If you go further downwind into the bronchial pathways, of course you need to be very careful, because you have thinner channels into the bronchial pathways, and if you are indeed tracking delivery of particles in those cavities, in those thinner cavities, generation 2, generation 3, generation 4, there should be enough elements in those cavities as well. So that is something that my students face difficulties with. They keep, say, a certain number, certain million cells in the overall mesh, but the mesh resolution is not fine enough in those finer channels. So in that case, either you do some regional mesh refinement, or you just increase the total number of elements in the mesh. Now, if you look at your printouts, I have already included the kind of scale factors and the maximum element size that we are using here. So for the scale factor, I have used 0.9, and for the maximum element size, I have used 1. Now, a CAD software is essentially, it is a dimensionless world. So what do I mean by 1? Typically, the scale would correspond to a millimeter, right? But then don't assume that every element here would be 1 millimeter, because that is not tenable. That's why whatever settings you introduce here, you need to still keep track of how many total number of elements are being generated, what is the overall volume that would give you the mean size of each element, and if you, based on the kind of venue journal that you go to, you might have to justify why you chose your mesh element size the way you have. And in fact, many times they would also ask for a sensitivity study. So let's go down. So let me enable the minimum size, and the minimum size that I have is 0.3. So once this is there, click apply, and the global mesh size has been defined. Okay, and then go to the next tab under mesh. So here we are setting up the parameters for the prism mesh. We are not building the prism mesh yet, but you can still set it up right away. So again, these numbers are there on your printout, and I think many of these are already saved in this file that I have opened. Now, couple of things to note here. You will see on the very second column that I have enabled some regions to have the prism mesh, but not the other ones. But if you read the names, curves actually contain the curves that are outlining each of these regions in the geometry. We don't need mesh refinement along the curves. We need mesh refinement along the left airway, especially because some clinical conditions like uh, allergic rhinitis, you might not know about the name, but that's a very common clinical condition, and there the inflammation happens along the outer parts of the nose. So we do need to, is the audio fine? Yeah. So we do need to include the prismatic refinement there as well. Left nostril is the plane through which the either the fluid or the particles are going in. We don't need refinement there because it is the inlet. So the left nostril does not have the refinement. Nasopharynx does, of course, for obvious reasons. Outlet doesn't, because there also the entire constituent is leaving the airspace. We don't need the refinement there. Right airway we do for same reason, and right nostril we don't. Tube, which is that extension that I have added at the base of the nasopharynx, I have enabled it there because what if the particles are depositing there? So we have it there. So let's press apply and then dismiss. Now we go to the last tab. Yeah, this is what I was worried about. It says network connection is unstable. So let's continue as long as we can. So let's go to this last tab. Now we choose, the default is tetra mixed mesh. So we choose that. The meshing method is robust octree. If you write journal articles, research papers using these tools, you need to mention these methods because they would like to see what you have used. And you don't need to do anything else here, just press compute. So now, based on how big your mesh is, it takes some time to get the mesh built. This one probably shouldn't take too long, but let's see. Sometimes for the 10 million, 15 million meshes, it can take, at most it would take 10-15 minutes, not more than that, but this should be quicker than that. No, this is not a solid region. This is just, so basically there is a cavity inside. This is not solid. This is just the shell. Yeah, 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 yeah. Inside is hollow. So you are building the mesh. So that is a very good question in the sense that some students do have their confusions with this. So for example, here it's a shell, the STL is a shell file. So basically, if you have something over here, if you look at the cross section, it is hollow. It is not solid, right? But if you are trying to use the same geometry for 3D printing, you need to make sure that the hollow space remains. But if you just print this, it would become a solid model if you print it. So then we have to figure out a region or basically a storage container which would contain that cavity, and that's what I did. If you remember the 3D print that I shared with you guys, I built an external structure like this, and then we meshed just this part so that the 3D printer would know what part would be solid and what part would be hollow. Okay. and we are building the elements, of course, in the hollow region because that's where you are modeling the fluid flow through, right? Funny anecdote: there was a student at SDSU. Of course, I will not name the name, but after working for 6 months with me, uh, building a lot of mesh files, suddenly came to my office. That, sir, I don't think this would work. I was like, why? Because I see the meshed model. It looks like the mesh model. Once I build the model, you'll see that. Let me use a different. You'll see that, of course, it is built of number of small elements, right? So her point was, this looks like a solid layer of bricks. How will the flow go through? So then and there, I basically pushed the student out of my group. So if after 6 months, you can ask that question after a day or two, at what is going on. But to ask that question after 6 months, that means that there is a very fundamental lack in basic scientific understanding. But that's a funny story. I'm not expecting anything like that from you guys. But yes, so we developed this mesh in the cavity, discretize it into the special elements, what CFD does, because there are some students in this, not many of you, but some who have not used CFD before. The reason why we do meshing, can anyone answer why we mesh? Why don't we simulate through the cavity?
Basically, we are solving the governing equation in discretized form. So once we have the discretized form of the equations, means that for each elements that is solved. So if we are just a large element, we do not mesh it, and that means that the moment we convert the algebraic equation into the governing equation into the algebraic forms, that is more accurate as soon as we have the small elements.
Yeah. Assuming that you are explaining it to your maid servant, what would be your answer then? Or maybe someone in your family who has no background in science. So all the Navier-Stokes equation, the solutions are easily tractable in known geometrical shapes, right? But these are complex geometries, and solving the Navier-Stokes equation is almost impossible in such complex geometries. So we are trying to develop some regular geometries, very tiny elements, regular geometries where we can solve the Navier-Stokes. Yes, it's a numerical solution. It is using all the techniques that we have developed. But at the end of the day, we are solving the governing equation in tiny elements with a known geometrical shape. And then we are getting the global mean of that. Right? That's the idea. So not for the fluid mechanics people over here, but that is what we do. So if we are trying to develop the CFD simulation of this room, we break it up into these tiny elements where we can solve the Navier-Stokes, and then we get the overall average solution through it. Okay, so I think the mesh has been, no, it is still going on. Yes.
What is the benefit of dividing into 3 or 4 regions?
Yeah, so that would depend on the question that you are trying to answer. So for example, if you are trying to figure out what is the, so let's assume that you are trying to track drug deliveries in this, in a constrained region like this. Then you have to develop a separate region on that. So you have to get the geometry into ISM, draw out a curve, and there is a way to do region partition. And you develop that particular region, name it to show up over here. And then that would show up on your fluent simulation as well. And you can directly get the deposition amount for that region. So for example, when I was doing some more clinical studies where we were trying to figure out drug delivery for sinus inflammation, there the target site is actually here, because if you think about the different sinus cavities, they are draining their fluids right over there. So then we have to develop a region right over here. We are not concerned about that clinical condition, at least for this geometry right now. What we are concerned about is as we'll show today, that the simulations that we are going to run would be both for infection mechanics and for drug delivery. And we are looking at treating conditions that primarily affect nasopharynx, which covers a lot of viruses. And that's why I mentioned the nasopharynx is not done. If you don't need the drug delivery of the pathogen transmission at the nasopharynx, you don't really need to get this as a separate part. Maybe you need something else, and then you keep that one. Of course, if you have extra regions, it doesn't matter. You have those, you have extra data in your simulation. Does it make sense? Okay, so the mesh has been built. So yeah, it would be easier to handle if you have a local computer, but over here, let me just use this. See, the total elements is 4052013, 4 million. So that was the gold standard that I was trying to hit. And that's how I got those meshing parameters, because initially I probably got something less than 4 million or sometimes more than 4 million. More is great for simulation, but of course if you are trying to numerically solve Navier-Stokes in as many number of elements, the simulation takes longer, right? So for example, this simulation, if I run it, it probably takes a day at most. But the full airway simulation with the 13 million elements, that took me, the computer was not doing as well, but it took me around 11 days. So it's a function of that. So it's the time cost prohibitiveness that you need to think about. But 4 million is fine for this one. So the next thing that, and this is the so if you look at your printouts, so we are done with this particular one, and this is the second screenshot is this one. This is exactly at this step. Yeah, the second and third ones is where we are right now. Okay, now let's try to develop the prism mesh, because the tetrahedral mesh has been built. So for that, we go back to over here, and we change it to, so basically we go to this one. So this is for prism mesh, and you are building the prism mesh on the existing mesh, and that option would show up because you are not doing anything with the tetrahedral mesh. You actually need it, but you are developing the prism mesh on top of it. Now, one thing that I do as a good practice, because the tetrahedral mesh might be useful sometimes as well. So I would suggest that before you develop the prism mesh, you save this. You save the tetrahedral mesh that you have already built. And before you save it, it might make sense to check the quality of the mesh. And you can do that by going to Edit Mesh over here. And this fourth tab, Display Mesh Quality.
Can you suggest any book where like you can get a clear idea of how to do the meshing, like means whether to use different mesh or with other meshes or
RF's book could still be useful in terms of the basic understanding.
other having full form?
Hassan Aref and S. Balachandar. Uh, because basically that is the book I like for all this. Yes, it is. It is just note it down. Hassan Aref. He is my academic grandfather, by the way. Hassan Aref and S. Balachandar. Search for computational fluid dynamics. Okay, so if I go to this fourth tab under Edit Mesh, Display Mesh Quality, and press Apply, you'll see that basically they classify the meshed elements in terms of their quality, how Now, how do I define as quality? It is how smooth the geometry transitions are from one mesh to another. Now, this is fine. The thing that we track is in the worst quality bin, which is the bottommost menu, if the percentage is close to 0%, which it is, but if it is not, there is a way to smooth the mesh as well. So, which you can do that by going to this fifth tab, and there is a smoothing iteration. You can do it some number of times. If you do it too many number of times, then you might lose some of the anatomical topological accuracy. So don't do that too many times, but you can do that as well. This third tab checks the mesh for any kind of errors. So these are the errors that might show up. You can read them, but the most common error that I have found happening is there is a hole in the mesh. Or when we have done the segmentation and we have built the geometry, there are some hanging elements. So there's some hanging part somewhere. The reason why this happens is when you are doing the segmentation, so let's assume that this is one of the slices because we are taking around 200 to 300 slices, right? So let's assume that in this particular slice, this was the airspace. In the subsequent slice, the airspace changed to something like this. Now, this element over here might not have, so if in second slice we picked such that that element does not have any continuation into this picture, a smooth continuation, this keeps on residing in the solid geometry, and it keeps on residing there in this 3D reconstruction as well, and it becomes a hanging element, and you don't want that. So you need to make sure that that is not there. So that is one source of error. The other source of error is when you do this regional partition, you'll see that sometimes some surface artifacts pop up which is inside the cavity, and you need to delete them. And some of these are software issues, and which you basically learn with using the software again and again. And I've had a hard time when I first started using it back in 2016. But that is something that comes
So
with
does it
practice.
show any written warning or you have to?
Sometimes you have to figure it out. You have to zoom in and figure out where the problematic elements are, and you can create a subset of those problematic elements and go back into that particular stage where you actually used that particular region and make sure that the pixel selection is smooth enough. Now, if you guys collaborate with me, thankfully that part we have dealt with already because these geometries are already built and we have around 100, 150 such geometries already built. But that is a painstaking process, getting that built. And in fact, like a couple of years back, a group contacted me to build geometries for BAT Airways, and the scan quality was so bad, the segmentation was not that straightforward, and there were so many hanging elements in there. Okay, so I'm not going to do the smoothing. Let me show you if I do the check of the mesh. So I press apply under the check mesh. So no problems were found for duplicate elements. And it is carrying out the other checks.
How we can check explanation of the explanation.
Uh, do you see that option here under the check mesh on the left panel? Could you repeat again? What error are you talking about? The skewness. The skewness. The skewness. The skewness is something that we can. So as you will see when I set up the prism mesh, there was a skewness factor as well, which has been tested to see if it works or not. So I don't think the skewness factor is there as an error option here, but that is something that we set up when we build the mesh. Okay, hopefully we don't get disconnected. Yes.
How we can select how many numbers of prism layers we
Yeah, so that's a good question. So that is also coming from our mesh sensitivity studies. You can pick 3 layers, 4 layers, and we have run studies where we have picked multiple number of layers to check if there is any difference in the eventual deposition data. So I think for this one I used how many? I believe 3 layers. Yeah, so I've used 3 layers with the overall height, the total height being 0.1 mm. But you can choose 4 layers as well. But based on the journal that you are going to, you have to justify what you are choosing, and you might have to run a mesh sensitivity study. Sometimes you can cite published works in this domain that this is what has been done and has been tested to work. Okay, so it's back. It's still going on.
So if we have the already tetrahedral mesh,
Yeah.
for that we are using the prism layer.
Yes.
Is it possible? Like, it may happen that already that it is a well-defined mesh, but it may get some unstructured after injecting the prism layer, or that is not the
It
case.
can happen. So we will do the mesh quality check even after building the prism mesh as well. Okay, so once the mesh quality check is done, you will get this diagnostics message, which you'll say yes, delete the unconnected vertices, because otherwise there will be an error in the mesh. So yes, and now the mesh is done. So let's save this. So save project as. So I'm going to call it GIAN 22 nasal cavity geometry, but as a good practice, what I do is just change the name of the last part of the extension. So this is a tetrahedral mesh, so tet mesh. And sometimes, as you see on the existing file over here, which you have access to, I also mention the number of elements that were there, especially when you are working, developing a number of mesh files. But let's keep it like this. Okay, so the tetrahedral mesh has been saved. The next part is building the prism mesh. So for that we go to this. So the prism mesh setup has already been built. That table that showed up, and if you go back there, just to review, uh, actually not everything has been set up yet. So let's set those up. So the maximum size is not there. So let's do that. So you can directly pick it from the by clicking on the item name, and the maximum size is 1. It would be activated on all the parts, but since you have already activated some regions where it needs the prism mesh, the other ones won't matter. Now for the height ratio, we are going to use 1. The number of layers is 3. The total height has to be changed as well, so let's change it to 0.1. is the height that spans those three layers. So that I'm picking as 0.1, sorry. And what else? We have the tetra size ratio, 1.1. Did we cover everything? So it's on the on the first printout that you have today. So 1, 0.1, 1, 3, and 1.1. Okay, so apply, dismiss, and then go to the last tab under mesh, and then pick the prism mesh and then compute. So folks who have used ANSYS before, did you guys, so the geometries were engineering geometries, or any irregular geometry like this?
These are regular.
Regular. But you did it as well, right? So what was your geometry like?
So links. Currently working on fluid structure interaction modeling of aerodynamic fluids.
Okay, okay. And did anyone here do ANSYS modeling? So these meshing parameters, they actually come down from different academic lineages, the academic families who started working on in this domain. So I'm not going to claim that everything was done by me. So many of the standards that I'm showing you here now, these are things that I've learned when I was a postdoc.
Like for example, in this we have a shop, and I have seen that one where they extrude the internal volume of the shell and then they latch it.
Okay.
Here we are not doing it that way.
What tool do they use for the meshing?
Formation only ICM.
I see.
They have just
Yeah. Is it a 3D mesh or a 2D mesh? 3D mesh. So the prism mesh typically takes longer because now the mesh is getting more refined in certain regions.
Why we are not using quadrilaterals?
Why we are not using what? Quadrilaterals? Yeah.
We are using it.
Like your question is why we are using tetrahedral mesh and not something else, right? There's no reason why. I mean, you can try it out with other kind of element shapes and check whether your results eventually they agree with the ones in literature.
Because that the quadrilateral is quite uniform.
Yeah, you can try other methods as well, other element shapes. I mean, there is no physical reason why, so that's why I cannot give you the answer. But these, as I'm telling you, that these are the gold standards that have been seen to work in terms of validating the eventual computational results with experiments as well. So when you use something else, you have to justify that the validation would still work. And sometimes it might be, it would, like if you're thinking about publishing those results, it would depend, of course, as you know by now, who reviews your papers. If that person knows the literature inside out, then you'll have to answer the questions like why you are deviating from what has been shown to work in this particular space. Okay, so as this one gets built, let me take the time to walk you through something else. So if you go back to the GIAN CFD simulation files, I have uploaded the protocols as well over there, so you don't need to remember everything from what we are doing. I don't think I have Acrobat Reader on this particular machine, so I won't be able to open it. But this meshing protocol, it outlines step by step the things that we are doing now. So when you try this on your own in the afternoon, you don't have to recall everything that I did now. You can open up that document, it's a PDF document, and follow the steps. Okay. So this is the meshing protocol, and I have the protocol for the flow simulation. This is the alias protocol, the last one. And then for the inert particle DPM method, the protocol is there, but we are going to do it both for drug delivery and for infection transmission. And for the way the particles are inserted into the domain, they are different in the two cases. So for the drug delivery application, the particles are going to go into the airspace in a conical shape. So there we need to figure out a point where the spray nozzle is located, and then we need to identify the coordinates of that point, set it up. We need to know what is this angle, and then the particles are going out like this. So this is for drug delivery. For the infection transmission, we are breathing in the aerosols, right? So there the particles are going in like this through the nostrils then. So although we are using Lagrangian DPM tracking for particle tracking, the way the particle insertion is set up is different for the drug delivery applications versus the airborne pathogen transmission application. Okay. Now, if I go back to this folder again, that one has all the protocols. The ISEM folder, in the afternoon, you can start from the nasal cavity geometry and test out whether you can develop this mesh, that thing that I'm doing now. But even if you cannot get to the meshing stage or the eventual output of the mesh, I've already saved the mesh file over here. So the mesh that I'm going to use is this mesh UNC071. That's the actual clinical identifier for this geometry, so you may note it down. UNC071 prism mesh is the one that we are going to use. So the mesh files would be in .msh format. So the mesh files that would be generated from this exercise would be needed in the first folder, which is the fluent folder. There also I have already saved the simulations. So the simulation that we are going to use is this one, nasal cavity prism mesh flow solve the 2021 same 30 liters per minute. There was some issue with the first one. It still worked, but there was an issue which I have mentioned in the lecture notes, but let's not get into that for this one. There was an error that I had to correct at the fluent stage. So we are going to use this 30 liters per minute 2021 simulation. So this is the flow field. Once you have the flow field, as we saw the workflow, the flow field is going to impact the particle transport. The particle transport is going to be inert and not impact the flow around it. So once the flow field has been saved, then these subfolders over here are the particle tracking simulations for respectively for drug delivery and pathogen transmission. So if I open one of them here, so this again, this second file over here, 2021 CM 30 liters per minute, this is the flow particle solved, which has all the particle generation information based on this particular setup, where all the particles are including through the nostrils then. So that is for pathogen transmission. For the drug delivery, it is set up with the conical injection that I showed. Now, under each of these folders, you will see that there is another DPM folder where I have saved the particle deposition data for just 10 micron particle. Of course, for a real work, you have to go through a whole range of particle sizes, but we are going to generate this 10 micron data, hopefully, and then compare that with some of the published works.
Micron particles are just treated as some points, or you, like, let's say you are putting like different sized particles. How are you assigning the size?
So the size dependence only goes into the drag force calculation because it's a function of the size, right? The diameter. But otherwise, because the particle cannot impact the flow field, it is a point particle.
You just put some points and then do random tracking.
Yeah. So you need to know the coordinates from where the particles are starting out from. Now, in terms of the pathogen transmission one, those coordinates are the centroids of the surface elements in the mesh. On the other hand, for the conical injection, because the spray is supposed to be inserted inside the airspace, you have to actually figure out what are the coordinates from where the particles are going to be ejecting out. And they are point particles, yeah. Now, for example, if you are looking at red blood cells, they are not spherical, right? So you can use user-defined functions to tell Fluent if the drag force formulation needs to be changed. There is a shape factor as well that you can control for those applications, but we don't need to worry about them here because we are assuming the particles to be spherical, and that is what the default is. It would assume that whatever that the diameter is, it is that the 10 micron is the diameter. It is a spherical particle, and it would calculate the drag accordingly. Okay, so this is the layout of the folders here. So even if you guys don't manage to do much on your own in the afternoon session, you will have access to all these files. And if you ever want to get started on this area, you can just run through these files. Yes. Yeah. If you don't do anything, it would by default assume it's a spherical shape. But then if you want to control the shape factor, you can do that using user-defined functions in Fluent. Now you can figure out what the shape factor could be for a different shape, whatever shape we are trying to track. But then again, there is this limitation: is that shape would get fixed. It would not deform because that is not supported under the inert particle tracking. Rigid particle with just a different shape factor, basically. Okay, so the meshing is still going on. I think we should be very close to getting done. So in terms of the protocols, I have included them. So if you go to the lecture notes file, that PDF, that big PDF, I think I have included the protocol there for the meshing, but I probably did not include the protocol for the flow simulation, which we are going to do later on today. For that one, you just access it directly from the protocols folder under the GIAN simulation files. Okay, so it is done. Let's now see how many elements are there. So you'll see that what we had before was 405 or 4.05 million elements. Now we have 4.45 million elements thanks to the refined layers at the walls. Okay, so we typically report this number of elements in our papers, how many elements are there. Now once this is done, we again go to edit mesh and we do the same exercise. We want to see the mesh quality. So if I opt for that, and now you see that there are quite a bit of elements, although if you think about the total percentage of elements in terms of the overall number of elements, it's just 1.3%, but still 57,000 is a big number. So let's see if I can reduce that. And to do that, we go to the smooth mesh globally. You can do it locally as well if you know the problematic areas, but most of the times using the global refinement works. So you can change these values. The default is 5 iterations until point 2. You can change this point 2 number as you go on. So let's first try with point 2. Apply. So I clicked it twice. So it really did not change much. So let's increase this to 0.25.
Maybe I was like respect to linear dimensional activities.
Yeah, it did not change much. Let's make it 0.3. And you don't want to go too much because too much of smoothing can actually, as I said, disturb the anatomical realism of the geometry. It is not changing much. So from 1.293% we went to 1.2%. I would stop it here, but for things like this, my advice would be to make sure that you report this in your work, that this is what the worst elements had, how many bad elements were there. Okay, so once this is done, we go to the check mesh again. And checking the mesh is critical because sometimes we build mesh, we output the mesh, and then we import the mesh into Fluent, and then Fluent tells us that it's a bad mesh. And that's unfortunate. Then you have to again go back and do this entire exercise again. So let's do the check mesh. And at this point, sometimes you see that there are problematic elements which you can create separate sub parts which you can fix locally. You might have to go back again to the segmentation stage and make sure that that transition from one set of pixels in one slice to the next slice where the same pixels are in the same region, that transition is smooth enough. So when was medical imaging discovered? All this medical imaging data that we are using, when was it first possible to get medical images? It started with the Ronaldo. It started with Wilhelm Ronsen, right? With Express. That's like early 1900s. It's probably early 1900s. Now, recently, I'm taking this time out because, and it could be part of the lecture. That's fine. But it would take a while to check the mesh. Recently, I came across this paper where this person. No, that was before that. So I was at a conference. I was at the DFD conference.
1895.
1890.
Won the first Nobel also.
Won the first Nobel. Yeah.
1901 he won. He is the first recipient.
Yeah.
Nobel Prize in Physics.
Yeah. So I was at the APS DFD a couple of months back, and some of you were there, right? Anyone here was at the DFD?
No, from Chandra's group, I guess.
Chandra's group. Okay. And at night, I finally managed to turn the television on. By the way, I'm very bad with technology. I have not been able to turn the television on in my guest house yet because it's a smart TV. So I don't know how to operate.
Maybe you have to turn the switch, but
I switched it on, but the remote is so futuristic.
The battery's got also.
No, the battery is there.
Okay.
Anyway, so I did manage to turn the television on in the hotel room, and the show that was going on was on Leonardo da Vinci or Da Vinci, whatever you might call it. And this guy, you know him, Moteza Kharib, Caltech.
Motivated.
So he ran some. So if you look at Leonardo da Vinci's sketches, he did a lot of sketching in different areas. Like for example, in my PhD thesis, if you access my dissertation, it is available through my website. My PhD dissertation was on vortex wake modeling, where you have a bluff object, wakes are formed. What is the most common vortex wake? The one common, with two vortices in each cycle. But as you increase the number of vortices in each period, it becomes very complex. So in my PhD, I looked at systems with 4 and 3 vortices. Uh, and Leonardo da Vinci actually drew some nice sketches where he showed these different smaller scales of in the wake structures, which is amazing because like he did not have a way to take high speed camera imaging, right? So I added that picture in my dissertation. But at that point of time, I knew, but I was not that aware that how much he has done about human physiology in terms of sketching. So when I was watching that show, I knew by then that he has done a lot of work. But Moteza Gharib is a turbulence guy, right? If I Devrananda Gharib does a lot of turbulence modeling, right?
Hmm.
Yeah. So he was focusing on the turbulent, the sketches on turbulence. But then I got interested and I came back and I purchased the notebook. That's what they sell it as. It's a big book like this thick of all of Da Vinci's sketches. And I wanted to see if he has done anything with the airway. And he of course has. So he has sketched the airway and the bronchial branching. And there is this guy, I think he's a doctor somewhere in Europe. He does some modeling, but since he is a doctor, he does not get too much into the fluid mechanics. So he did some modeling, but looking at those sketches, it is amazing. Like he did not have access to any kind of medical imaging, right? He probably just did some cadaveric sectioning and drew those images. So
He had this famous picture of like large like amount of water falling in from a drain falling into a tank and all these large eddies, small eddies.
small it is.
Yeah, because there is no concept of even turbulence that time. But he just observed the whole flow process and like today we can see tell that the turbulence is like a large from a big scale to smaller scale that so many vortices appear. But in his like he is starting with the largest eddy, then like the smallest eddies are appearing.
And
It's
he just observed those streams and he does not have a snapshot in time, right? He just looked at the overall averaged visual data and drew those sketches. So if anyone here wants to write a paper which would get noticed straight away, pick up Leonardo da Vinci and pick up whichever system you are comfortable with. Figure out the corresponding sketch from his workbook. Try to develop the digital model of that. Run some analysis, run some CFD, and there is a very high impact paper for you. So I was telling
there
my
was
friend,
a scientist called Troy Singor. He also visited OS. This is some Rutgers University basis or something. He like once he has a few science and nature papers. He said like he does fluid mechanics and many other things also, but mostly classical physics. So he said like occasionally I look up some papers of Lord Rayleigh and Lord Kelvin and then work on it. It turns out to be still there are many interesting things which can
yeah,
be explored.
yeah. So yes, if you ever run short on ideas, this was a big fear that I had when I was at your age when I was finishing my PhD. That I'm being guided by my PhD advisor. The ideas are primarily coming from him. So what would I do when I'm on my own? Uh, but if you ever feel like that, just purchase the Leonardo da Vinci workbook. Okay, so we are, I think, close to getting done here. So delete the unconnected vertices again. So yes, and the mesh quality is fine. And I'm showing it here just as an exercise. Of course, I have already built the mesh and they are available for you. Now to generate the mesh, we go to the output mesh tab and go to the first option here. And this would let you generate the mesh in different package softwares. So Fluent is of course there. What else is there that might be interesting for you guys? So Star CCM Plus, is that anyone here uses Star CCM or on this campus?
Mostly
No.
as this, maybe some solid like use, but they also use Avocas.
Yeah, Abacus should be here as well, I think. No, it's not there. Anyway, so ANSYS Fluent is what we are going to use. So apply and then go to the last tab over here. Oh, I have not saved the project first, so let's save it. And I don't want to overwrite anything, so let's close it now. And so it's going to change a few things. That's bad. So let's do it this way. So save project as. Now let's call it GIAN 22 Prism Mesh. Another way to get new ideas, I know all of you go to conferences now, right? So as PhD students, one big mistake that I used to make was just attend the vortex dynamics sessions, because vortex dynamics is what I used to do. Try to attend other sessions as well, because if you just stay within your own very small subfield, you don't know about what is going on in the other fields. So especially when you go up as job candidates in the academic domain, it is important that you know what is going on overall. Okay, so let's now output the mesh. So this is
After that,
okay. Output mesh and then go to this last tab. The project has been saved, so no. Now you pick the corresponding file. So this is this file. So open. Now, if you don't do anything at this stage, the mesh would be named as Fluent. We don't do that because then things get confusing. I would copy paste this BOCO file and use that as the mesh name. And done. So now if you go back to your the directory folder that you are working from, which in our case is the GIAN CFD simulation files, ISM for CAD. So you see that this file is getting built. It is going to get bigger as long as it shows up here that it is growing. You see it is growing. So that's what we do to develop the prism mesh, and the prism mesh that we are going to use or you are going to use in the afternoon. You can use this one that we have just built, but you don't have access to this, right? You will have the ones on the cloud folder. So use the one called UNC071 Prism Mesh. It's exactly the same as what we did today. Now once the mesh has been built, we will import it into the Fluent to run the flow simulation. So in the next session, we can set up the flow simulation. The other thing that we need to do, which needs some ICEM work, is figuring out where this location is for the drug delivery application. Where is the nozzle placed? And to do that, that would occupy one session. I should not do that for the sake of time. What I will do is I will open the work that I did and show you how it's done in broad stroke. I think all of you are smart enough to understand how, if you have to do it from scratch, how it should be done. So in the second session, we will do the flow simulation, and then in the hopefully in the following session, I'll show briefly how to get this one done, and then go directly into particle tracking. We'll do particle tracking, get the data, and then go and compare that with published papers. Now, what are the timelines that we have today? Let me think a little bit because today is somewhat different.
Can you assume 2 to 3 and then what is the poster session? 4 to 5.
Yeah, 4 hours.
Okay, okay. You
So
can,
my target would be to
maybe you can start like, I don't know, 1:30 to 2:30 and then 2:45 to 3:45, something like that. And then whoever wants to go to that your conference can go.
so what my intention would be to show the work, or do as much of the work that I can show you guys and do it on my own.
Yeah,
Because
so you
once
can just like now it is just 1 hour gone. Then maybe like we can also like extend the next session by 1 hour 10 to 15 minutes just
okay.
to be more biased.
I mean, I would like to stop at logical time points. So basically, flow simulation, I will stop it there, and then do this part, and then the particle tracking. And if there is time, then we can compare the data with the literature data. But if we don't have time, then keep it for the subsequent session. But what I was hoping, that I think I was misjudging how long time, how much I would need to get these things done, because I'm explaining certain things to you guys, so it's taking longer. So even if you don't have much time to do any work on your own, I think I'm giving you enough cues so that if you are interested, you can do it, and you can get in touch with me anytime you want. So let's continue this way. In the next session, we are going to do the flow simulation. file, and it has been done, and you can compare the sizes. So it is to that level. Now let's now go into the Fluent simulation, how to set that up. So before that, let me close off the ICEM window, and the project is already saved, so no. So this Fluent that I'm using is the 2023 version. What is the version you guys have here? 19. And I have used 19 fairly recently as well, so whatever files that I have should be fine on ANSYS, on 19 as well. Okay, so as you launch Fluent, this is a 3D simulation. Find double precision. Depending on how many processors you can use on your machine, let me use 12, but it's of course a function of the system you are using. So on a typical laptop, personal laptop, 4 processors should be fine, stable enough. So start. I think the Fluent layout changed drastically from the 15 version was very different, and then it changed drastically, and then otherwise it has been very similar since then. Okay, so now the software is launched. The first thing that we have to do is bring in the mesh file. So let's go to file, read mesh, and let me go to the corresponding folder where I have this work. So lab data. So I'm picking this UNC071 file. Okay, so now the mesh is in the Fluent platform. The first thing that we'll do is check the mesh quality again, because still at this stage you can find some errors and then the simulation won't work. So check mesh, and I think it is done. It did some improvement on the pathline tracking, particle tracking. That is not relevant at this point. It's the flow simulation that we are going to develop next. Go to scale under the general, because this is funny. Once everyone in the has Chandan visited here, Chandan Bosch. Did you guys attend his talk,
I
Chandan?
visited online lecture.
Online lecture. Did you attend his talk?
Good.
Chandan Bosch.
It was clapping. Once he was
Yes, so
doing
Chandan is our junior from JU Des. So Chandan does open form modeling. So we decided that we should collaborate, and I shared one of my geometries with Chandan, and he was supposed to develop the open form simulation and was supposed to compare the data with the fluent work. Now, of course, he was done with the simulation, and then we started to track the data, and it's as we found out, the pressure drop needed to generate similar flow rate was very high in open form. Can you guys guess why that was the case? It shouldn't be the case, right? Because of the dimension. So when I said that the CAD software, the ICM, is dimensionless, it just does not tell you whether it is in millimeter format or meter format. We know from experience that the length is equivalent to a millimeter. But when you import that mesh, or you export and then you import that mesh in your computing platform, you don't know about the length scale. So Chandan did not change anything on that. And as a result, what he was modeling was what you have over here. So right now the Z direction is basically this direction from the front of the nose to the back, and the dimension comes out to be around 100 meters. So it's a huge person. Like I think Devrananda yesterday was telling me of Professor Shanku's story where the human being got tremendously big. So it is that big of a person. Have you guys read Shotajit's Ray? You haven't. So basically, if you think about the pyramid as the tip of a nose, it is probably as big as that person. So you need to be careful about the scale, the length scale, and that is something that if you are working with other comparing platforms, whatever that conversion length scale is, you need to be really careful about. Otherwise, even after months of hard labor, things don't go to anywhere. So over here, go to specify scaling factors, make it 0.001. We are trying to convert to the millimeter scale, and scale. So now see what shows up. So 0.114, 0.115 meters. How much is that? 11.5 centimeters, right? So if you think about the dimension of your own head, 10, 12, 13, 14, 15 centimeters is what you get. And make sure that what you see on the screen, you don't trust it blindly, but it is physically realistic because you are developing a biological model. So now that has been set up, and of course the scaling factor should be same on all x, y, z because you don't want to give an aspect ratio to anything. So once that is done, close, and then this is going to be a pressure based solver. So the flow is driven by the pressure gradient. Should it be steady or unsteady? Based on our understanding of the mathematics from the first few days, unsteady, right? So that is key towards what we did yesterday, that in the upper respiratory tract, the time varying component is strong, and that should dictate what you choose over here. If on the other hand you are trying to model transport in the bronchial generations, if you are past that conducting phase, you can use a steady state simulation. And typically, if you do read the medical journals where they do this kind of modeling work, they never really explain anything on this, and I can assure you that most of the times they would use steady state simulations for upper respiratory tract. But we are not doctors, we are the useless kind of doctors. So we need to make sure that we understand the physics and apply the simulation accordingly. So transient. And after this, you can turn the gravity on. I do turn the gravity on, but as I said yesterday, the gravity effect on the flow flux is minimal. It becomes prominent with the particles. But since my eventual goal here is on drug delivery or infection transmission, I'm going to turn it on. But if you are coming across a problem where you are not tracking the particle transport. It is just the flow simulation, some kind of heat transfer effect. That is a very big area of research as well, where we have some papers too, where you think about the flow going through the complex pathway and how is that warming up the air. I think we were discussing about this couple of days back. The nasal passage is very tortuous, so when we are inhaling the very cold air from outside, the air gets warmed up before it reaches the lungs, and that is a heat transfer problem. There, you don't need to turn the gravity. But since here the eventual goal is to get the particle transport data, let's turn gravity on, and then you can assign what direction you want the gravity to be. So again, this setup is, as you probably recall from my slides from yesterday and from some of the lecture materials, if this is the nose, I have the Z direction from the front of the nose to the back, the Y is up, and the X is into the plane of the screen. So based on this, the Y should be negative 9 point the G value. Now, there are again some clinical studies where they have found that if the person has some kind of sinus inflammation, we want to send drugs to the maxillary sinus, which is that big sac on the two sides. So the doctors, they recommend the patients to lie down on the side and then apply the nasal spray. If that is the case, then think about what the corresponding direction of gravity should be. So this person is then lying down. So basically, it is oriented in the X direction, and you can control that from here if you are trying to model drug delivery when the person's head is inclined in a different direction. But here we are just trying to get the normal condition when the person is walking, sitting upright, and negative 9.81. So this is all for the general model. Let's now go into the fluid mechanics modeling. We are going to set it up as an LES model. So viscous SST K omega. I do remember the individual numbers, but just in case, I don't think I have the protocol here either, so that's fine. But you will find the relevant parameters that you have to set up on the LES simulation protocol. But over here, let's go to large area simulation. Now, what subgrid scale model would you use? Have you done LES, like the mathematics of LES modeling in any of the CFD courses? You have.
No, actually, I think Douglas wanted to get the course,
Yeah,
but it's lost before they have already finished the questions.
I see.
Most of the people, so it's lost last year.
Okay.
Most likely they have.
So what LES model does in very brief, if I try to describe it very briefly, it develops the general flow profile, but it needs the support of a submodel that would resolve the smaller fluctuations. So along with LES model, you have to choose a subgrid scale model to resolve those fluctuations. Now, it is up to us what to use. What we do is use the kinetic energy transport model. But then again, you can look up each of these models and try to figure out why you should be using which one. I do plan to use the well model next because what I found out from my attending different other sessions at the conferences, that the well model could be equally potent, if not stronger, for geometries that are very complex as we have over here. But for the timing, we are going to pick kinetic energy transport model, and that is what we use in our published works as well until now. So click OK. So this error comes up because of a certain reason which I'm going to show later on, but it is automatically changing the numerical method to something else. I'll come to that in a moment, but let's click OK for now. Okay, so the viscous laminar, let me just quickly double check one more thing. Yes, so LES and kinetic energy transport model. Now let's, so the discrete phase option over here, we have to set it up accordingly when we do the particle tracking. We are not doing the particle tracking yet, so we don't have to worry about it. Let me see if I can make it bigger. So the discrete phase is for particle track. Let's not change anything over there. Let's come directly to the materials. And under fluid, we are modeling air. Now these are the generic density and viscosity values for air, outside air. We are modeling air that has been inhaled in, which is typically warmed up. So based on literature, we would change the values. The density should be 1.204 and the viscosity should be slightly higher, 1.825. And then change, create, close. Now let's go down. Let's come to the boundary conditions. Double click on the boundary conditions. This is the inner material, the meshed space. We don't have to do anything in there. Left airway is a wall. We can keep it like that. For you can check what it means. So if you go to edit, it shows up as a stationary wall with a no slip boundary condition. If you want to apply some kind of wall effect, you can do that with UDFs at this point. I'm not going to change anything. Now later on when we do particle tracking, this DPM option is going to show up. And there you have to figure out whether the particles should be trapped at that wall or reflected or do something else at that wall. Since we have not set up the DPM here yet, that does not show up. So this is fine. Close. What we need to be careful about at this stage is what are your inlets and what are the outlets. And especially this gets a little confusing when you have the mouth included, the oral cavity as well in the model, but this one doesn't, so that is easy. So the left nostril is actually the plane on the left side of the nose. So that is going to be an outlet. So that is wrongly defined here at this point. So we are going to change it to pressure outlet because it's a pressure, sorry, it's an inlet. So that's where the air is going in through. So it's a pressure gradient driven simulation. So pressure inlet would be left nostril. And then as you change the kind of wall, this shows up. So you can assign the gauge total pressure, which is where if you are doing something else in terms of your pressure specification, you can assign other values as well. But as I showed during the lectures, it doesn't really matter. It is the delta P that matters. So I'm going to keep it as it is over here. So apply, close. The nasopharynx is wall, fine. The outlet is the outlet at the base of that tube after the nasopharynx. And I'm going to change it to pressure outlet because it is again a pressure gradient driven simulation. Having said so, from our experience, we have found out that if you have very thin channels, sometimes the outlet vent option might work. When you actually, instead of the volume flow rate, you actually specify what is the mass flow rate through the system. But for now, on this simulation, we are going to change it to pressure outlet. And now we have to figure out what should be your gauge pressure. It is going to be a value that is smaller than the one at the nostrils, right? Because high pressure to low pressure driven flow. I would suggest that use some trial value, say negative 50 pascals, but you use the targeting. So target mass flow rate, you specify that, and then figure out what should be your targeted mass flow rate. Now in this work, we are trying to model 30 liters per minute. So 30 liters per minute. Wrong one. So we have to convert 30 liters per minute to What is the unit over here? It is in kg per second. So we have to convert that to kg per second. So the rho of air is 1.204 times 10 to the power of minus 5 kg per second, right? That's what we picked, right? For the density of air, let me just quickly check. So go to the materials, air, 1 kg per cubic meter. Sorry, this is density. Sorry, my bad. So this is the density of air. So you have to use this to figure out what would be the kg per second rate for 30 liters per minute. Let's go to where we were. So the conversion should be, if I'm not wrong, 30 times 1.204 divided by 60 times 1000. So 60 for the minute to second conversion, 1000 for the cubic meter to liter conversion, then 1.204 is the conversion from volume to mass. Can you give me this number? 0.6 into minus 3 kg per second. So 0.0006 kg per second. So we can set that thing up over here under the targeted mass flow. So 0.000, how many zeros? 3 zeros. So 6. So this is where you change when you are trying to simulate a different flow rate. Then you press apply over here. Okay, just to double check, let me see if it got activated. Yes. Is it 3 zeros or 4 zeros? 3. Okay, now 6 times 10 to the power of minus 4. Yeah. So right airway is still wall, right nostril is not wall, so we have to change that as well. So it is where air can go through as well. So pressure inlet, and as you change the wall type, this window pops up and it is also at 0 gauge pressure. So apply and close. The tube is a wall, it is the tube at the base of the nasopharynx. So all good with the boundary conditions. You don't need to worry about anything until the reference values. So the reference values, I personally consider it to be a good practice to update the values over here to what you are using for the material property. So 1.204 and 1.825. Okay, so that's there. Now come to the methods. So under the methods, we are going to use Simplec and let's keep everything second order. But one thing that I did a mistake on a few months back with one project was for the transient formulation, you should use either second order implicit or the bounded second order. So I think I have updated the protocol accordingly. Don't use the first order implicit because there could be some errors. So let's use bounded second order implicit. And in fact, now with the more recent versions of ANSYS, they also given a warning like this here. The current turbulence model should only be used with bounded second order implicit. Okay, so let's go to the controls. This is all fine, but for example, if you have heat transfer going on in the system as well, then from this equations menu you can pick the thermal equations as well. Let's go to the monitors and the residuals. So now you have to figure out the residuals for the proper convergence, and then for that as well you need to look at literature to figure out what is the accepted standard. So for the continuity residual, we are going to use. Uh, could you guys open up the protocol? It should be oh, 10 to the. I don't think it's 10 to the power of minus 6. It's a mix of 10 to the power of minus 4 and 10 to the power of minus 5. I don't remember which one. So I don't think I printed this protocol, did I? No. So let me remember. So this is 10 to the power of minus 5, the continuity. If I am not, 10 to the power of minus 4 is continuity, and the x velocity, y velocity, those are. Yes, so this is 10 to the power of minus 4, the velocity components, and the continuity component is 10 to the power of minus 5. You can pick 10 to the power of minus 6, that's fine. Even with picking so small values, you will see that sometimes the simulations don't reach, the residuals don't reach those orders. But if they stabilize, that's all that you can get in terms of convergence. So let's close it here. But when you run the simulation yourself, do take a look at the protocol for the correct values if I'm wrong here. So okay, and then 10 to the power of minus 4 for continuity. And what about the velocities? 10 to the power of minus 5. Okay, so 10 to the power of minus 4 for continuity and 10 to the power of minus 5 for the velocities. Okay, now let's come to the initialization, and there I would use the standard initialization and compute from, you can pick any of the inlets. There are two inlets over here, both the left side of the nasal airspace and the right side. You can pick either of the two. Let's pick right nostril and then initialize. I hope something is going on. So the the fluent simulations that you guys have done, what kind of flow model did you use? Okay, SST. What about you? And there are some studies where they compare all these different kind of turbulence frameworks, like which one is suitable for this kind of geometry. Typically, it doesn't take longer. As long as this, I think there is a lag in what we see on the screen, and something is going on. I trust that it worked at the back end. So let's see if we can now start the full simulation. So over here, let's think about the time steps that we are going to use, and there are a couple of papers on what you need as the proper time step size. There were a couple of publications back in the early 2000s, 2010, 11, where they looked at geometries as complex as this one, and they tried to figure out the best possible time step, in the sense that longer is the time step, quicker would be the simulation, right? If you're trying to track a certain interval. So for 30 liters per minute, the 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 consensus was the time step should be point triple zero two. Sorry, yeah, you're right. So the time step size is over here, right? Yeah, 0.00. Sorry. And now comes the number of time steps. So typically, you have to decide what is that interval of time needed for the flow to stabilize in the airway. You can pick any number of time steps. The simulation that we are going to use for the particle tracking, if you open it up, you will see that I have used 1750. So what is 1750? Think about 1750 multiplied by 0.0002. It is around 0.35 seconds. So that's the interval of time I used to consider that the flow to be stabilized in the airway. And based on the size of the airway and the flow speed, which is on the order of meters per second as we saw yesterday, that is sufficient enough. And of course, that number, the choice of those numbers are backed by other papers that have been out. For now, to show you how it feels like once you start running a simulation, let me just pick a very short, small number of time steps. Let's just pick 50. But of course, you are going to pick something much bigger. And then go to, I think the rest, the iteration. You can change the iterations as well. If you make the iterations fewer per time step, it's again going to be a quicker simulation. Point triple zero two. Yeah, yeah. So calculate. So now you'll see that there are two windows, console and the graphics window. So this is the console where the residuals are going to show up their values. But if you go to graphics, visually it is easier for me at least to keep track of what is going on. So this is going to evolve. And there would be fluctuations, of course. But after a certain period of time, the fluctuations would be within a certain range. And that implies that it is going closer to stabilization. But still, as a good practice for our published works, we always maintain that high number of time steps before we use the simulation. So this is anyways going to stop after 50. So it's already at 23.
Sir,
Yes.
total time for the airflow is like breathing inlet breathing time, that is 3
No, the time that I'm imposing over here is the time it's needed for the flow to be stable in the airway. Now the breathing time interval is different. We are not tracking that aspect of the process. We are looking at a snapshot in time how the flow field has developed once it is well developed. But if you are trying to think about that time varying effect, no, we are not capturing that. And that is going to be on the order of, so the total breathing in, breathing out is around 5 seconds. And that I'm not discounting your question in the sense that that is something that could be studied as well. Like what happens if we run the simulation such that we cover 5 seconds? That would take long. That can take on the order of, with the computing powers that I have, if 0.35 seconds take a day, think about how long 5 seconds would take. We can do that. But the thing is, once the inhalation phase is done, uh, the way the particle is coupled with the flow, we are trying to get the drag force, right? So the flow goes up and goes down. We cannot use the field when it goes down. We have to use the field in the mean region. So that's why we are taking this value once the flow is well developed. But you are trying to simulate the whole inspiratory phase. That has its importance, maybe for heat transfer, but not for particle transport. But on the other hand, if you develop a two-phase simulation where you are where the particle impact can impact the flow field, then you should probably think of it as a 5 second flow or a 2.5 second flow for the inspiratory cycle and see where the particles go with that. Because now it's a two-phase system, right? Does it make sense? But then again, the computing demand would be much higher. So something to think about in future. Yeah. So this is going on. I think where are we?
They have those periodic spikes, I think.
The periodic spikes. I don't know numerical artifact. You know better than me.
Rahul, do you have any idea? Why do these periodic spikes?
related to studying what things.
Steady you don't. Steady you see a smooth curve overall. And these spikes stay. They run in there, but eventually it fluctuates within a certain range. Okay, so we are done with 12% of the simulation, which is so what it is going to do is 50 times 20. So it is going to go till 1000 over here. So we are till 124. So it's going to go till 1000. So it's going to take half an hour or so. Let's not go till that. But the thing is, you now have a good sense of how the simulation has to be started, right? And you can follow the protocol to do that. So you get the mesh file imported into Fluent and start the simulation. And you can then, once the simulation is done, this is important for especially folks who have not used ANSYS Fluent before. Go to File and then Save Case and Data Files. Case file is the one that includes the mesh information and the numerical setup that we have built up. The data file is the data that is going to be generated. Okay, so you have to save both case and data files, and that is available from this file menu. So File, Save Case and Data. I'm going to close this simulation now. How long do we have in this session? Till when?
When it started, 11:15. Half like 20 minutes.
Okay. So let me show you something else from the simulated file now. Okay, let me just close it. I should not take up this computing time on my machine there. So I'm closing the simulation, but I'll open the one that I had saved on your cloud folder. Okay, so now to open a saved simulation, which you can do because I have already saved the simulations, go to File, then Read Case and Data. Before, when we were just including the mesh file, right? Importing just the mesh file. But here, since you have the data simulated already, so Case and Data, and go to the, let me go to the GIAN simulation files. So, and the folders on your cloud folder, they have the same names. So go to Fluent for Sims, and this is the flow, just the flow field. So don't go into the subfolders, just pick this one, this last one, and okay. So although in that pop-up launch window, just the case file shows up. But since you already chose case and data from Fluent, it would also pick up the data file as it brings the information in. Funny thing, Devranjanda is my PhD roommate now works for ANSYS.
Okay.
So he's in sort of like maintenance, those kinds of things. So he
Does
he
he like look into the algorithms also?
I think so. I don't know the details of what he does now, but he worked with an out and out computing guy at Virginia Tech.
All the things which we dismiss as artifacts, they may have little more to offer. So
Yeah, let me see if I imported the correct simulation. So to get the output data, so there's some simple things that you can directly get out of this window. If you go to reports over here, so go to flux and then the mass flow rate. So the left airway, sorry, not the left airway, the inlets and the outlets are left nostril, right nostril, and the outlet. So compute, close. So what do we see on this window? I hope you can read them. So basically, this is the air flux going into the left nostril, point 0.000329. This is the air flux, point 0.000268, going into the right nostril. What does that tell us to begin with? The flow is asymmetric. To generate a 30 liters per minute flux through the tracheal outlet, through the nasopharyngeal outlet, the two noses, they contribute differently. So sometimes based on the study that you are trying to pursue, that itself is a very important information, how asymmetric the two sides of the nose could be. Now this net is not important. It is just they are trying to sum it up. The other important factor is the outlet, and the negative sign is important because there the flow is escaping the numerical domain, so hence the negative sign. But you see the value that we have achieved, 0.00059. What was the targeted value? 0.0006. So the simulation has worked. Now sometimes it might not work. Sometimes you might end up getting a value which is more than what the error could be more than what you probably can sort of accept. So let's assume that you got a value which is 0.22054. That would be hard to publish on, right? Like you cannot really validly claim that 0.22054 is 0.22006. So then you might have to redo the simulation, make sure that the pressure values get changed a little bit, and you can also do a convergence, an interpolation study, as in you can run two simulations, figure out which particular pressure values led to what kind of flow rate, and then you can interpolate those pressure values to figure out at what rough value of the pressure drop you would get a 30 liters per minute flow. But we got lucky here, and many times we do get lucky, and we got a outlet flux that is 30 liters per minute. So you should save this particular window every time you do this kind of work. And from here, the other thing that I would like to show you is this is the flux. Let's look at the pressure drop. So for that, go to the surface integrals, and there the report type would be area weighted average, and again pick the left nostril, outlet, and the right nostril, and then compute. So now these are the pressure drops. Again, there is asymmetry between the left and right sides, and then the outlet is something negative 27. Because we used targeting in our scheme, it did change from negative 50 pascals to something else. Now, we also have to report the delta P. To report the delta P, what I do is I take this absolute pressure at the outlet and figure out the mean of this other two, and then subtract that from here. So let me go to your printed pages, and there is an example of this, but it's a different simulation, the one that I have included in the printed pages. But can anyone show me the page if you can find it? Not this one. So basically, it's this one. Yes. So you do understand how we get the delta P, right? But let me just show you over here. Okay. So the numbers are different to what we found in the simulation, because when I was preparing this lecture note, I was using another different simulation with a slightly different kind of a mesh. But the concept is still same. So this, just for the sake of record keeping, let me show the conversion. So this is in kg per second. So this is 0.00059836736, and I'm converting it back to liters per minute. So this should be multiplied by 60 times 10 to the power of 3 divided by 1.204. Can you give me this number? Huh? 29.81. So 29.81 liters per minute. So very close to 30 liters per minute, which is what we wanted to achieve. Now over here, so that is the flow rate, which we typically report as the first thing, and then from here we are getting the pressure drop. So we have the outlet pressure. So this would be delta P, which is minus 27.52 minus half of the two other pressures. So 19.31 plus 2.19. Actually, this would be plus, right? Because you are going to get the delta P. So what would be this number?
minus 38.27.
No, it cannot be
There's the plus sign.
there's a plus sign. Yeah,
minus 16.
minus 16.78. Now, once you run the simulations yourself, I would like you guys to update these numbers because the numbers would be different because this simulation had an error, which I later on found out just before traveling. But the generic way, the way we do the calculation and report the data is like this. Now, these are some streamlines from the same simulation, from not from the wrong simulation, but from this simulation that you have set. So, the things to note could be connected back to what we had studied for the first few days. So look at what the velocity magnitudes are. The range is 0 to 5 meters per second. It starts out with something which is very close to 0. So on the order of 1 meters per second, let's assume. And the maximum it gets is 5 meters per second. Now, if you remember one of the problems, I had assumed the flow to be 5 meters per second. Here is the justification for this, but also with 1 meters per second, as we found, even if the flow is slower, the problem that we were trying to solve was how long does it take for a 100 micron particle to deposit, and we saw that the time interval is so short that it is going to deposit in the anterior parts of the nose. Okay, so you can generate this kind of visuals as well based on what kind of post processor that you might be using. I am not going to go into post processing in this course. uh, Different groups have different favorite processes. What we do is use field view, in case if you want to know the name, but you can use other processes as well. By the way, what post processor did you use? Techplot. Okay, so this is the flow simulation. Now, if I go again back to the simulation here. mm, so this is so do run the calculation with these numbers later on. So the flow simulation is saved. Now we are going to use this to do the particle tracking. Let's stop here, right? It should be close at 12:15, right? 12:15 is the closing time.
Fine.
Yeah. So in the next session, we are going to first show how to figure out the location of the nozzle if you have a nasal spray, and for that we have to go back to ICEM for a brief while, and after that we are going to come back to the fluent vault and set up the particle tracking, run some quick particle tracking simulations, get the data, and for that you guys have to do some calculations as well on some of the printed sheets, and then we are going to compare that with some published paper. I think we can get it done in 1.5 hours, but maybe comparing with the published paper could happen in the last session. And then, based on your availability, you can head over to the CAD lab and test out the files. Okay, so does that sound like a plan? Okay, so let's wait for now. Thank you.
So meet at 2 again here. Good luck, great
So in the last session, we ended with the flow simulation, and we saw how to extract the pressure data and the flow rate. So the next thing that we need to do is the particle tracking, which, as I said, we are going to do it both for infection transmission as well as for drug delivery. But before that, let's get done with the remaining ISM part, which is figuring out the parameters that we need for the spray nozzle, and we would need that information for the simulations. So for that, if you look at your printed pages, essentially it will be first this page over here, and so the second one is this one. So in the first one, in this page, what we have here is, and I have shown this briefly at the talk yesterday, the CU protocol is the current use protocol, which is what they recommended. They recommend in the over-the-counter spray products that you need to tilt your head slightly in. So think about the head being tilted slightly in, and the spray bottle goes in vertically into the airspace. What we propose is, if we can reorient the axis of the spray bottle so that it hits the septum directly, then probably we can improve on the targeted drug delivery for the, sorry, it hits the nasopharynx directly, so it can improve the targeted deposition at that site, which is the nasopharynx. Now, either way, we need to figure out where the spray nozzle exit is, and that's what we are going to do. And this is a screenshot from the ISM, and you don't need to worry too much about this screenshot. We will be doing that anyways here on the screen. And I'll come to this one in a moment, but this is what we get as output from the ISM in terms of the spray axis and where the spray nozzle is located. So let me move over to ISM here again. So on your cloud folder, by the way, I heard that the 2023 files are not opening on 2019? It did not open? Which one did you try to open? The flow simulation? So did you try any of these files? 2023 file will not open in 19. Okay. So what I unfortunately we don't have any 2019s anymore. We had it in one of the computers in our lab, but we don't. So what you do is, if you really want to follow through on this, is open up the mesh file. The mesh file will open. It's .msh. So just like what I did this morning, open up the mesh file and develop a new simulation, because the protocol is still valid. Okay, so let's go back to the ISM folder. Now, for the spray axis determination, I have created, it's not only spray axis determination, it's also the location of the nozzle. I've created this subfolder just to avoid confusion. So let me open this one. Again, if the ISM files don't open on the 2019 one from 2023 version, I have all the information for the spray axis and the nozzle location, so you can directly use them. You don't have to do this work. And the first bit of work that we did this morning, developing the mesh, that mesh is also there, so you don't have to worry about using ISM as such. Okay, so this is the geometry that we had this morning, but I have done some modifications on the geometry over here. So instead of going through each of the steps individually, let me just describe what was done. So the idea is, in terms of the spray axis, Let me make the screen, make the surface transparent. And let me make the curves thick. Okay, so what you have is, let me go to the view and then left. Okay, so I think this gives a nice view. So over here is the centroid of the nostril plane, this particular point. And from this point, I tried to get a direction that hits the nasopharynx directly. Now the nasopharynx is so far back that if you take any point that is further downstream, this axis will be blocked over here. So think about a direction. Think about that you set up the target point, say over here in the nasopharynx. Okay? So if I put the point here, then the direction would be like this, right? So as a result, what would happen is the spray axis hits the cavity walls right over there. All the particles would be trapped there. So that cannot be an effective direction for targeted delivery. So you need to have an open region through which the axis does penetrate into the airspace by at least a little bit. It cannot directly hit the lateral walls, or for that matter any other wall. Because of the inertia of those particulates, they would just deposit over there. So that's why the best possible choice is to pick a point which is as high up as possible, right near the edge. And then you get the direction from the centroid of this plane to that point over there. Now, functionally, in terms of how to get this, sometimes these CAD softwares are unique in their own sense. I don't know of any clean way to get the centroid of a plane on ISM. Unlike, I think, SolidWorks probably directly gives you the centroid, but I might be wrong because I don't know SolidWorks that well either. So what I have done is, this gray plane that you see on the left nostril, I have rotated the plane about centroid by certain angles and kept the copies of that. Let me just show you this particular part. So let me do this. So I'm hiding the points and the curves. So let me deal with this particular plane. So what I did was go to this particular tab, the square with the yellow arrow, and this is the select option for whatever geometry you want to keep, but select this and then click on the region. Fine. And then no, let me just cancel this thing a little bit. So again, go to the square with the white, go to this option over here, the second option where you can rotate the geometry. So click on that. Now you can pick any axis to begin with. So let's pick the x-axis. 90 degrees is fine, but make sure that the plane that you are about to rotate now is going to be rotated about its centroid. You can rotate it about the origin of the overall space or about any other point. But since I'm trying to figure out the centroid, the idea is to get it rotated about the centroid, because eventually the intersection point of those transformed planes would give you the centroid. Keep the copy option open because you don't want to rotate the original plane. That should stay like where it is. And then use select geometry to pick this. And then the way the mouse works for ISM is the middle button does the trick. So select enter entities with left button. So you can, the first time you're using this, you can follow this instruction over here, but the next step is press the middle button and then press OK. So you see that I have created a new plane that has rotated, but it also cuts through the centroid. But just one transformation is not enough. We have to do two of them because we want the intersection point a single point, which is the centroid. So for that, let's go back to the same step, but now let's rotate the original plane about a different axis. So let's pick Y. Still make the rotation above the centroid and go here and here. Middle button click. Okay. So now yeah, so this is a nice view. So this plane is cutting through here and the other plane is cutting through here. So the centroid is located somewhere over here, and you can see that clearly if I put the old centroid that I had. So make it large and let's make the surfaces transparent. So that's where those transformed planes they intersected each other and we got the centroid there. So this is how it was done. Now if you end up using ICEM there, of course I cannot teach the entire software to you in 10 minutes. You can figure it out. You guys are smart enough to figure out how things are done. So for example, this tabs that you have at the top, I have to deactivate the transparent because otherwise the overall system becomes very slow. So all these tabs, this first one is related to anything that you want to do with points. Whatever iteration on the geometry you think you can achieve with points, you basically go to this one, and it has a number of options. You can go through browse through each of them to figure out what they do. The second option is for curves. Anything to do with curves. You can use curves to break up a region to solve something that you ask, like how to create new regions. You use a curve to break up an existing geometrical part. The third option is for surface. So anything that you want to do with surface, if you want to connect two surfaces together, make it into one whole surface, or if you want to break the surface up into two parts, you can do that as well. But I won't go into all those details right now, but many things can be done. The other thing that I did was, once the centroid is there, I have to figure out what is the where the nozzle should be placed. So for that, so this, can you see this green circle over here, green point? So that is where the nozzle is placed. The understanding also comes from literature that the spray tip should insert into the airspace by a distance of 5 millimeters. So that is the algorithmic way of saying that we are shallowly inserting the spray nozzle into the nose. So this distance is 5 millimeters in the direction from here to that point. So we first fix that point, we put this line, and then we use the direction cosine of this line to go 5 millimeters in the same direction. And that gives you the nozzle location. So for example, if you go to,
Lesson pointer there in the classroom, that classroom, just asking.
I am curious as well. I need to go through my backpack if it is there, but otherwise it could be in the classroom. We should go stuff over. So let me show you. So basically I have some data over here on the printed page. So let's go over there. I should have saved the lecture notes on this computer, but it's okay. Okay, so this is the same geometry that I'm dealing with here. The nozzle centroid are these coordinates, and I got these coordinates. If you right click on the point on ICM and you ask ICM to give you the point info, you will get the coordinates, and I can show you in a moment how to do that. And these are the centroid, these are the coordinates of the centroid. So this, but before I got this one, the first step was to get this particular direction built in the ISM. So let me write down some comments just for clarification. So this is the spray axis intersecting the target site. And this, of course, we know very well by now is the nasopharynx. And the understanding is we took it so far high up because otherwise, if I had picked a direction that goes like this, then that spray axis would hit the nasal walls very early and would deposit all the particulates over there. We do want the axis to penetrate without any kind of obstruction, at least a little bit into the airway. So this is the spray axis. And this red point is the nostril openings centroid. This distance is, as I said, 5 millimeters. Now, that itself could be an interesting study. Some people have done some work on this. So we have this as the centroid, this as the nozzle location, right? It's not that this nozzle location is on the periphery of the gel. You do realize that, right? It's just that perspective view. It is inside the airspace. Now, if you take a point which is further in, say 10 millimeters into the airspace, obviously you will get better drug delivery because you are starting the particulates further into the airspace. Question is how realistic that is. How far deep you can put the spray bottle inside your mouth, inside your nose, the spray nozzle. So there is the discomfort issue as well. So there have been works out there in literature where they have taken deeper locations for the spray nozzle, but just so that you know, this is the standard protocol. But we can use a different distance as well. Okay, so this is the nozzle exit position inside the airspace. And just so that it is clear to you guys later on, this is the left nostril plane. Okay, so once you have this particular direction, we can get the direction cosine. So I think I have a code for this. And this code is trivial as such, but we are getting this information from ISM once you have fixed these 2 points and created this particular. Yeah, so basically you need, once you have this point, the centroid point, and you have the point on the nasopharynx, then you can directly get the direction cosine of the direction which we need for the simulation. So this is the code. It is already saved on your cloud folder. These are the 2 points and magnitude, and we get the direction vector. So the XYZ components of the direction vector, we need this for the simulations. So that's why if you go through your lecture notes, I made this comment. Okay, so this is the direction cosine, which you can check the MATLAB code. Now, in terms of the information that we will need to run the drug delivery simulation, those would be the nozzle location coordinates, so this information, and the direction cosines, so this. And along with that, for drug delivery, so this is, I'm talking about drug delivery, right? We don't need all these details done for the infection transmission work. The other pieces of information would be the cone angle. So I think I have some printed work for this as well. So if you look at the manual for ANSYS, the way they define the angle to be plugged into the system, it's the half cone angle. But unfortunately, they are calling it the cone angle, but it is half of that hollow angle. So we would need that information. I have that information from you from measurements that we have done before, and I'm going to comment on those later on as well. So we need the cone angle. What else do we need? We need the exit velocity of the particles from the spray nozzle. And that exit velocity again have been measured experimentally, and we have plenty of data that's our work as well as people have published on them. Typically, the number is anywhere between 5 and 20 meters per second. So for the work today, we are going to assume 10 meters per second is the initial exit velocity of these particles. Anything else? So you have the cone angle, you have the location of the cone, you have the initial speed, and we know that we are going to run the simulation over a range of particle sizes, but for the work today, the particle size is going to be 10 micron. Okay, so this is the extra work needed on ISM for the drug delivery work. Now let's go into particle tracking. Any question on the mark?
Is that how we can ensure that if the most whatever the drug carrying that does not trigger in that accident?
What do you mean?
Instead of the the sample which contains the drug.
Yeah.
So we need to inject it.
Yeah.
So at which
Okay. Now I get your point. So, did you read the papers that I had asked you to read last night? Okay, let me show you something from there. So your question is, yes, we found this direction cosine. It's a very precise direction. How do we ensure that when I place a spray bottle, it is in that direction? So there is this gap in relaying this mathematical information to actual practice, and that is a challenging gap. So there are several ways how you can navigate this. So let me show you one example here. So this is a paper that I published in 2020, and it was on the improved use versus the current use protocol. Towards the end, we thought about this question that you are raising. So this is actually one of the co-authors on this paper. So she was holding the spray bottle, and this is the so-called improved use direction or the line of sight direction. So we collected this picture of her, the inside of her nose. Now once the doctors know that this is what can be seen from the line of sight direction, the doctor can actually advise the patient that hold the spray roughly in this direction. You don't need to be precise, because also what we found out, and I showed yesterday, that this is the perturbation study, that if you change the direction slightly, still the drug delivery maximizes for the same size ranges, and it does maximize compared to the current, it does increase compared to the current use conditions. So still you are going to get an improvement, maybe not the best possible improvement, but still some improvement. And healthcare, patient care is primarily disbursed by the clinician, right? We are not in that space. What we can give them is a mathematically precise ideation of the problem, and then they have to figure out how the patient can understand this. So this is one way we thought could work, and I believe the doctors who were part of this study, they tried to use that, and that worked. That okay, take the spray bottle, put it inside your nose, and then make it as horizontal as possible, and make it slightly tilted on the outside towards the cheeks, and that seemed to have worked, and that is this direction that you are seeing. So whatever work you might do as a biomedical scientist, for that matter, eventually for that work to be useful, you need to talk with the other community, in this case the clinicians, and once they understand what you are talking about, maybe they would find a way, a qualitative way to explain that to the patients. Does it make sense? Okay, let's go back to the simulations again now. Okay. So this is clear, right? So I can close this. But the details of the work, if you ever have any questions with ICM, you can contact me. If I am unable to help you, I'll connect you to one of my students. They probably know it better than me. Okay, so let's close this. Now we are going to get into the fluent particle tracking. So for this, as we know by now, we are using the flow field. It's already there. It has already been simulated, and we are going to develop the particle tracking next to it. So let's close this. Again, the particle tracking protocol is there. Does anyone have the protocol in front of you? Keep it handy because I sometimes tend to forget some of the criterion numbers. Okay, so 3D double precision 12 process start. Now, while we get started, as you probably can recall, the extra work was for the drug delivery for the surface injection, which is for the infection transmission. When we are breathing in the aerosols, the particulates, we don't need to do anything else. So which one do you guys want to do first, drug delivery or infection transmission? Okay, drug delivery. Okay, so either way the flow field is same, drug delivery or the infection transmission. So let's go to read. Now I'm reading the flow field in, so read case and data. And this is not where our files are, so when is that conference that some of you have to go to? When so when are you planning to leave from here?
At 4 only, because there is some time before that.
Okay.
It's fine, you can keep the break for 15 minutes instead of 10.
Yes, sir.
So 3:15 to 4.
No, like it has been half an hour, right? I'm trying to get at least the particle tracking done by 3. Or in fact, can we extend till 3:30?
Yeah, and go at this pace.
Okay. So the flow simulation is in. Now for the particle tracking, the main change that happens is first we have to change the model or add to the model. So we go to the model and then discrete phase, injections. Yeah. So these particles are going to interact with the continuous phase. So you click this option and the rest is fine. Now on the protocol, I think, do you have the printed protocol? Anyone here?
You can access.
Okay. Uh, I think this is 10 to the power of 8. 6. The maximum number of steps. So 1E06.
Step length factor 20.
Yeah. 1E06. Six. 20. And then under the physical models, because these are tiny particulates, they can experience some lift force cross stream, and that is the Safman lift force, which is something that I did not discuss in the theoretical derivation. But from my understanding of literature, this is sometimes included, sometimes not. The effect is minimal, but I had included it in the simulation that I've shared with you guys. So let's include it. Yes.
Actually, I read this assessment. This is generally used like connected to the sleep velocity.
Sleep velocity.
Like the particle with respect to the flow.
It is connected to the slip correction, right? Basically, when you have the small particulates, that CC correction that we are doing is connected to that. So basically, when you have the small, very small particulates moving cross stream, now the question is, what do you define as small in this context? Now, since the idea is for drug delivery or for that matter, any of these applications that we are developing, we start from typically we start from zero point 0.1, zero point 0.2 microns. That is quite small. And then we can go till 30, 40, 50 microns. They are big enough. So this correction, this slip correction or the lift force effect are probably not that relevant once we go beyond the 10 micron, 20 micron mark. But they are probably relevant in the 0.1, 0.5 micron scale. But since we want to use the same protocol for the entire project, for the entire problem, that's why we are using it basically. Okay, so now let's go to the numerics. This is 8, right? And the refinement number is 20. The maximum number of steps was 10 to the power of 6. Okay. Okay. So let's okay this. Now let's go to the injections and create. Okay, so this is going to be a solid cone injection. So go to cone. Inert particle anthracite is fine. I don't worry much about the name. I just need to make sure that the material properties are chosen accordingly. Now we have to put the location of the nozzle where the particle is going to start out from. So now we can use this data that we had and put in the actual numbers. So we have the nozzle location coordinates of 15. Do we need to do any change of scale here? So these coordinates that you see are from the ICEM world. Remember? So that was in mm, while in Fluent we reside in the meter world, and we did that rescaling when we brought the machine. So we have to do this rescaling for these coordinates as well. So this would be 0.0, correct me if I'm wrong, 0.015, 3215. The y position should be 0.039, 2498, 0.039, 2498, and then the z coordinate. Devranjendra, think about how we get the bad habits. I am calling it Z in India. The first time I got to the US, so they don't use the word Z, they call it Z. So when I was a first year graduate student, I was like, what is this guy talking about Z? But now I am doing the same thing. So 0.023, 2432. Now for the diameter, we are going to test it as 10 micron. So 1e minus, sorry, 10e minus 6. So the azimuthal angle stay as it is. It covers the entire spherical domain. The x-axis, y-axis are the direction cosines. So there, the units don't matter. They are just dimensionless. We know that. So we have minus 0.0157, 0.4054, and then 0.9140. Right? Oh, sorry. Now let me quickly check the cone angle that I have used in this work. Okay, so the cone angle that I had used was, that's again the half cone angle, right? So it's half of that angle, half of this angle here. So I'm talking about this much of the angle here. Now the total angle can vary anywhere between 30 to 70 degrees based on measurements, and those measurements are mostly collected with laser diffraction studies. Do you guys have any laser diffraction setup anywhere here? Laser diffraction. So they pass a laser sheet as the spray is going out, and they can get both particle size distribution and things like cone angles. So
Maybe there is
that could be a valid platform for collaboration, because right now the work that we are doing is with a company. Yeah.
people actually working on spray diagnostics they typically try to measure the drop size distribution.
Yeah.
So yeah.
Okay. So the cone angle is 30 is what I had assumed, but as you can tell, there is a range, and each spray product would have a mean value, and we can test that. The actual value could be for one of the very popular spray products in the US. The value I can remember right now is 31.16 degrees, that half cone angle. The velocity magnitude 10, again coming from literature and the laser diffraction studies that we have conducted collaboratively. And the total flow rate initially, or at the particles, the flow rate coming out of the spray nozzle is supposed to be very low, and we just use the number that we have. Let me just check the rest of the entries. So 0.01329249.8.0. Okay, so everything looks fine. So let me okay this
Total flow rate is in kg per second for the particles.
for the flux coming out of the spray nozzle. Nothing to do with the flow field.
In the spray, they are just the particles acting.
Yeah. So we cannot keep a zero value. Then there would be an error. So we keep something which is very, very small. Okay, so let me close this. Now the tedious part that comes here is now setting up the boundary conditions appropriately. Thankfully, we probably don't have too many regions in this one. So the left airway is wall. It would be a trap boundary conditions based on the work that I'm trying to show here. So go to edit. Now the DPM thing is open. Sometimes they have very odd things already default into the system. Reflect does not make any sense, because if the particle gets reflected from the interior walls, then where are they going to go? So this is going to be trap, apply, close. And you probably would want to double check that the boundary condition, the wall condition was done correctly, because I remember once there was a postdoc who was working for me. She kept on telling me that none of her simulations are are ending. They're going on forever and ever. Can you guess what happened? Because she was keeping reflect boundary condition everywhere. The particles were getting reflected and reflected and reflected and never ending up anywhere. So that's a postdoc. So now left nostril. This is where the particles are going in. The DPM over here, what I like to keep is reflect, and that is the default. Like if some particle do manage to hit the plane, which it should not, because they are all being pushed into. But if it does, then thanks to inhalation, they will be sucked back in. So let's skip that. The nasopharynx. Here the DPM should be trap. Again, the reflect has to be changed. So my guess is she never bothered to go into and change the boundary conditions, and everything was still reflecting. Let me double check that it got changed. It did. Now for the outlet, the DPM should be escape, and that is what it is, so that's fine. For the right airway, by the way, if some of you might have some experience with ANSYS, you can copy the boundary conditions from one wall type to another. I am old school, I don't want to do that. I just need to make sure that everything is correct individually. So this is the right airway, so trap again. Right nostril, I would put it as reflect. And reflect it is, so that's fine. And the tube is that region underneath the nasopharynx, so I'll keep it at as trap. Now the reflect could be quite interesting sometimes, and we did run this project once. Think about a tortuous channel. So think about a system where you have something that's going like this. A bioinspired system maybe, where the particles going in, they're not trapped straight away. They have very high inertia and they get reflected. And then they go further into the airspace, and then they again approach the wall, and then they get again reflected. This could be physically realistic as well in certain sense. Over here we have the sticky mucus that can trap the particles in, but in other engineered systems we might not have that kind of hydrophilic nature to the surface. And we did come across this once, and the experiments were being done at a different group, and the experimental data mismatched with our numerical results, and then we have to actually use the reflect condition and make sure that the wall conditions are accurately mimicked over here in the simulation. But since the mucus is sticky, we don't need to worry about that. This is a trap boundary condition even at the tube. So apply, close. So I think we are ready with all the boundary conditions. The rest of the things should be fine because it already has the simulation data. Now let's go to reports, and actually for the particle tracking you have to go to plots, and let me correct again, you have to go to graphics. They have changed with each version, they changed this thing a little bit. So okay, so go to the particle tracks now. Here is where we are going to do the particle tracking. I'm going to generate a summary file which is called the DPM file for this tracking. So go to summary and file, and this injection 0 is where we had the cone injection saved. We had missed one thing. Can you guys think a little bit and tell me what we have missed? We have set up the particle sizes, we have set up the cone, and we have set up the boundary conditions of the walls. We have not told ANSYS anything about the formulation of the material properties. So that we have missed. So we have to fix that. So let's close this again. So let's go back and materials, solid. Uh, the discrete phase is on, so this should be fine. Let me quickly check something. Okay, so this is fine. Okay, so now if things have been set up fine, I somehow the discrete phase got turned off, so I could not find this inert particle option here. Now this inert particle option is there. That's where you need to change it. So anthracite is what the name of that material was in the injection setup. The density should not be that high. So let's assume that these are watery droplets. So 1000 is what the density is. We are going to use a different number when we track the infection transmission mechanics, because there we are not breathing in water particulates. We are breathing in dehydrated respiratory ejecta. The particulates that have been dehydrated have lost the watery components, just carries the non-volatile proteins and the viruses. So there the density would be 1300. So make sure that we do that. But now this is drug delivery, so 1000 is fine. So change create. Close. So I think now we are ready to do the tracking. Let's go further down next. So we come to graphics, particle tracks, summary, file, injection, write. Now where would I write this? Let me create a separate folder for this. So we are saving the work under Fluent. So this is drug delivery. So actually let me just keep it here. Okay, so summaries, file, injection, write. Drug delivery, DPM, because these are DPM files, and 10 micron, but let's call it GIAN 22. Okay. So because these are 10 microns, the tracking should be pretty fast. Let's see what it saved, if it is useful or something else happened. No, something went wrong. So let me just go back. There cannot be just one particle. So the error probably is at the stage of the discrete phase modeling over here, because that's where I faced something else. Yeah. So the error was over here. This number of streams are the number of particles that are going out. So this is the solid cone that we are dealing with. Now, how many streams of particles are there? You have to define that as well. And the default was 2, and I forgot to change that. And that you have to change. So you can use as many number of particles as possible, with the caveat that if you pick, say, 10,000, 500,000, there could be someone can ask you, what about the particle-particle collision? You are not including that in your simulation. So again, do read papers in the literature, see what people have done. So 5,000 is what I'm going to use. And yes,
If you fix the mass flow rate you specified for the particle,
yeah,
so wouldn't that will quantify how much particles are moving?
no, no. They can assign as much to those two particles, because it is not that mass flow rate is a non-zero number, which has nothing to do with the particle sizes as such. It is just creating a continuous flow. So that has nothing to do with what are the particle sizes. That 1 times 10 to the power of minus 20 stays same even if I pick a different diameter, with the number of stems being the same. So okay again, and let's try this again. So particle tracks. Let me just close this file. Okay, summary file injection 0, write. Let's name it with the same name, and okay to overwrite here. The very small particles, the 0.1 microns, 0.2 microns, they take a long while to run because they traverse the entire pathway. The bigger ones, they take shorter. So this one is done now, I think. So let's go back. Okay, now we have some data that could be relevant for us. So we have, so if you can interpret the data over here, what we have here is the number of particles that got trapped at each of these zones. So this is on the left nostril. So 412 particles were trapped on the left airway. On the nasopharynx, 1725. On the tube, which is downstream from the nasopharynx, 55. An outlet means 2088 particles, 2808 particles, they escaped further downwind. Which is the number of interest for us? The nasopharynx one, right? That's where we are targeting. So let's now do some work. Somehow the printed sheet has a different number, meaning that I used a different simulation for that. But that's okay. So let me now move to this screen. Unfortunately, I just have one USB port on this machine. To get out of this computer, go to here. Okay. So the number that I had was, if you see your printout for nasopharyngeal deposition, was 1684. The one that we got just now was 1725. So let's just carry out the calculation with the current number, and you can update this as and when you do your own work. So this is the calculation of targeted delivery efficacy. Yeah, so calculation of the targeted delivery efficiency at the infection point site. In this case, that is the nasopharynx. So therefore, this is equal to the number of particles deposited at the nasopharynx divided by the total number of particles, right? So the total number of particles administered times 100. So numerator, number at the nasopharynx, denominator, total number entering the airspace, and you can track that. So this is the screenshot from the Fluent console window that we had 5,000 particles of that size. That being the case, so we have the number of particles deposited as 1725. The total number of particles is 5,000 times 100. Can you give me this number? 34%, right? So 34%. So this is the efficiency for 10 micron particulates. So this is the efficiency for 10 micron particulates for spray targeting at the nasopharynx. Question is how realistic this is. So that's where let's try to compare that with some published work. So over here, I think we can just keep on using this particular. It's clean enough now. So we are talking about. So in this one, we looked at left nostril. That's where what we did, figuring out the nozzle location, right? We were in the left nasal airspace. So this is the left nostril, the data for left nostril, and the flow rate was, what was the inhalation rate? We did that before lunch. What was the inhalation rate? 30 liters per minute. So let's go to the paper. This is the paper that I asked you guys to read. So basically, if I just quickly give you, this is not that paper. This is the 2021. No, not that one. It's the one from 2023. So this is the Akash paper 2023, where we are looking at these two geometries. So the first geometry is the geometry that we actually used since morning. So it would be subject 1 in the data. So let's go to the paper. So subject 1, it's figure 6 on that paper, on the Akash paper. So subject 1, left nostril, correct. So it should be the first column. So left nostril is the first column. The breathing rate, the inhalation rate is 30 liters per minute. So that is this second row. So we are getting the data for 10 microns, correct? So let's do this. It's going to be a rough estimate. Of course, you can make it as accurate as possible. So this is where it's cutting. So how much is the value on the, how much did we get? 34%. So you can see the number. You can do it more accurately than what I did here. But that is basically around the same number, right? So although I did use a new flow simulation, because the moment I change the mesh a little bit, as we run a new flow simulation, things change. The flow rate is not precisely the one that was used in that particular paper, but you get still the same order of magnitude, basically the same value. So now, do you feel comfortable enough that you can actually run this kind of drug delivery studies? You need to get an anatomical geometry, set up the simulation, and of course it will take more time. You need to track whole range of particulate sizes. You probably need to add more breathing rates. But based on whatever we have learned since morning, you can do this, right? Any questions? So do make it a point to browse through this paper to get the full benefits out of this course, so that you appreciate how it can be used in a broader context. And this is the approach that we take in our collaborations with the drug delivery companies to improve their product performance, be it for the formulation design, be it for the delivery device design. Okay, so that's all for the drug delivery. I think if we get half an hour more, we can finish up the infection transmission right now. So, what do you guys suggest? Okay, Debrananda, let's continue.
Yeah, the source of truth is
Okay. So, for the drug delivery studies, let's again go back to the remote. Yeah, so if you're writing down your lecture notes, just make it a point that check, compare with data on figure 6 of Akash et al. 2023 Frontiers in Drug Delivery. So this is going to be just so that you know which subject. So this is subject 1 in that paper for 30 liters per minute and for the left airway. Now one good news is I think if you guys you probably definitely missed it, but on my slides yesterday I said that Akash is looking for a job. He is about to graduate, but last night I heard back from him that he has received an offer for postdoc in the US. So he should be graduating soon. Okay, so let's now move on to the infection transmission work. So the particle setup for the inhaled transmission of pathogens is much easier. There you don't have to worry about the cone angle. You don't have to worry about the spray nozzle location. Anything. You just need to set it up as a surface injection. So let's work on that. Now this fluent simulation is here. To avoid resetting the boundary conditions again, let's see if we can just modify this simulation to a surface injection, and let's see what happens then. So we will to modify it, we of course have to go back into the injection thing. So injection 0, it was a cone injection, so let's change this to surface injection. So the moment you pick a surface injection, answers would want to know which surfaces would embed those particles that would be entered into the airspace. So which surfaces should they be? Where are the particles coming through into the airway? Huh?
It is an inlet.
Inlet. Which are the inlets here? The left and right nostril, right? Now, based on the problem, if you have the oral cavity, you might want to include mouth as an inlet. Whatever you pick, there should be a justification for that, and you need to explain. And mouth might not make sense when you consider the fact that we breathe less than 10% of the time through mouth. Okay, so left nostril and right nostril, surface injection. Let's pick the same diameter. So 1e minus 5 is 10 micron, right? 10 micron. The flow rate stays same. The x velocity, y velocity, z velocity. So for that, I believe I have included some instructions here, but What we are going to assume is these are particles that when they're starting out, they are at rest. They are static. They are getting the velocity of the fluid. We are not assuming that. So when we breathe in, the particles get sucked in based on the airflow velocity. Otherwise, these are aerosols that are suspended in air. They don't have any ejectile velocity as such. They are not moving around. They are not self-propulsive in that sense. So they don't have any velocity of their own. So we don't worry about any x velocity, y velocity, z velocity here. This is the diameter, and this is a non-zero value that we still could be using. Inert, left nostril, right nostril. Okay, so let's close this. But now we have to redefine the material property, because initially we thought that those inert particulates were for the drug delivery application. They were water droplets. Let's change that. Let's go to under materials, inert particle, anthracite. So now, as I said, these are particulates that, let's assume that I am sick. I'm giving out aerosols. The aerosols, the moment they go out, they get dehydrated. And if he is breathing them in, he is breathing in the dehydrated particulates. They are heavier than water or more dense than water. So there was this paper which I cited in my talk, and I think I have shared my talk as well on the cloud folder. So this paper came out from NIH in PNS in 2020, Stadnitsky. So they did those measurements. It's around 1.3 gram per cc, so 1300 kg per cubic meter. So let's change, create, close. Okay, so the rest should be same. Let's go down. The boundary conditions are same at the walls. Now go to particle tracks. So when we set up the surface injection, there is no option to set up streams, right? So what they do, what ANSYS does is, once you have the surface injection, it looks at the surface that I have defined that the particles are embedded, and looks at the corresponding mesh. I'm drawing it very simplistically, whatever the mesh is on the surface. It picks the centroids and embeds the particle at those points. So this, how many number of particles would be tracked, hence becomes a function of the mesh. Wider the nostrils, more particles will be tracked. But on an average, I have noticed that any adult human being, the nostril size is such that for the mesh refinement that we tend to use, we get around 3000 particles on each of the nostrils. I think so. Well, 3000 both sides together. So left and right nostrils together is 3000. Anyway, so let's go to the particle tracking. So summary, file, injection 0 is now redefined, right. Let's go to the infect the pathogen transmission folder. DPM for pathogen transport, 10 micron, but let's add to that state. I've been writing Jan 22, right? It is Jan 23. Okay. So now the particle tracking is going on. So it's done. You will see on the console that the number of tracked particles is 3015. That means there are 3015 particles shared between the two nostrils. Let's go to the corresponding DPM file. So it is under fluent for SIMS, pathogen transmission, DPM pathogen transport, Jan 23. Okay, so now what do we need? We need the nasopharyngeal data, right? 399, which is again slightly different to what we had because we are using a different simulation on a different mesh file, but still of the same order. Anyway, so what does incomplete mean? Incomplete means those particles have not landed anywhere yet. Trap means left airway, is trapping 1067, but let's just focus on this nasopharynx data. And let's move to the document viewer now. Let me share another funny story to make things interesting for you guys. And Debranjula, this is a eye opener for us as well. So there was this student uh, who did a lot of work. According to him, he did a lot of work. He did not save any of these DPM files. He was just looking at the data and putting things on the Excel spreadsheet, and claimed that he is getting some things that are striking and things that probably I did not expect. But he did not have any of the backup data, and his claim was, "Who cares? Who is going to look at the backup data?" I was like,
Okay, so he copy pasted DC to Excel sheet.
he
But
copy
he
pasted.
didn't check his
So
original
if he's just tracking the nasopharynx, he just copy pasted this number,
file.
and there is no way to check back whether that number was actually the correct one or not.
Anyone can claim in just put those.
Yeah, those could be fake numbers, and with GPT in this era, you can generate those data, this kind of data. Giving a basic trend, you can generate data. So always make sure that you follow good practice, good protocol, and especially when you become professors in some years, some of you would be professors. Make sure that your students follow through with this with the Reaper.
Nowadays, actually, all these websites are like the journals are saying to share the original code or the data.
But still, there could be some gap in surveillance, in the sense that people are sharing data, but are they sharing all the data? That's the point. So make sure that when you are running simulations, save as many files as possible, all the backup files. Don't just take things from here and go to spreadsheets. Okay, so let me go to this thing now.
And so like in this manually way, you mentioned in manually pick up the center mesh to locate the initial position of the partners.
What do you mean by manually?
Like you mentioned that this way is like we have to manually select
No, no, no. I meant to say that the ANSYS does it for you. So when you identify the surface, it directly picks up the locations of the centroids of each of the elements on that surface as the starting point for those particles. You can of course define the particle locations yourself. If you want to do that, you can do that. But if you don't do that, if you just set it up as a surface injection, it looks at that surface, looks at the coordinates of those mesh elements, and then picks the centroid. Okay. So I'm going to use the number that we just got because that's what we have been doing today. So let's just use the number that we got. So before that, let me note down a few points. So over here, the density is 1.3 gram per ml. So this is mimicking dehydrated respiratory ejecta expel by an infective carrier or host. The ejecta is initially water dominated. For example, the sputum in our airway is 99.5% water. So it is initially water dominated and then undergoes prompt environmental dehydration before being inhaled by an exposed subject. So that's the idea. Of course, these are precise enough measurements for this times, but things could be improved as we gather more precise data. Now, the total number of particles tracked is 3015. So that's between the two nostrils, and then the number of particles depositing at the nasopharynx is 399. So therefore, calculating the pathogen droplet deposition efficiency at the infection trigger site, which is the nasopharynx in this case, so number of particles deposited at the nasopharynx divided by the total number of particles administered. I would not say administered because that sounds like a drug delivery. So total number of particles inhaled in times 100. So this is 399 number of particles depositing at the nasopharynx divided by the total number of particles inhaled is 3015. Can you give me this number? Huh? 13%. Okay.
I think we have just noted on the profile which I wrote 5,000 if I'm not wrong.
No. The 5000 was for the drug delivery one. This is here the total number of particles 3015 is. So for 10 micron particulate for this particular model, we see that 13% of them would be depositing at the nasopharynx. So let's compare this with the published data. So for this, if you read the papers, you need to look at this paper that I wrote in 2021. So here I was trying to track the infection transmission mechanics for COVID-19, but again, the geometries are these two geometries. The first geometry, which in this paper I'm calling it as AR1, anatomic reconstruction 1, is what we are going to track. So AR1 is that. So that plot is here. So AR1 is the first set of color map, and where is our data? Our data is for what is the breathing rate again now? 30 liters per minute. What is the particle size we tracked? 10 micron, right? So 10 micron is over here. So this is where we are. So 10 micron and over here. So what is that value? So if you connect it back to the color map over here, it is not as yellow as over here, but it is more than that. So somewhere in over here. What was the percentage efficiency you just got? So that matters. So now you guys should be ready to lead a study like this as well, where you generate the anatomic reconstruction, develop the flow simulation, and then, of course, there is more work involved. And I was still too naive, so what I did was, I think I did both RANS best SSTK omega and the LES. I did both in the same paper. You don't really need to do that. But here you go. The result matched up from the work that we did today. So I had this printout for you guys, which if you can see, this is 10 micron, this particular one here, which is around that number, 13%. Okay, let me note down the the figure number on the notes for future. So compare with data on figure 3, panel A of figure 3 for 30 liters per minute inhalation in AR anatomic reconstruction 1 of Basu scientific reports 2021. Okay, I think, do you guys have any questions on all this? So from where we started, the basic theoretical formulations, and then we did some computational modeling, and coming back to the actual translational application, does it all make sense overall? Okay, so I would hope that at least some of you from this group, this might not be your current project, that's fine, but in future you might get to work on these topics. Yes.
And the same things like the same like kind of protocols, but like when we like release the like multiple droplet clouds during cough and sneezing, so there are also like the large droplets tend to drop earlier. So that kind of like over which distance, how much drop, like the distribution of the droplets over the distance,
Yeah.
that can be used using this kind of
Yeah. So actually, let me show you something here. Uh,
because in that previous paper there is some schematic of the cloud, like the coughing or the sneezing.
yeah.
It's like you are releasing some sort of turbulent clouds containing multiple size droplets, and then
So we published a paper on outside of the human body. So let me show you. So this is for to track particular transmission inside a classroom. So the team was led by actually a pharmaceutical company, and Boston University, they were involved as well. But we did this. The main contribution from our group was this figure. You are a mechanical engineering student from JU, so you won't appreciate it. But this is a classroom which is not very clear on the projector. But this is one of the classrooms from a civil engineering building. That's where we had our final year of classes. So they collected the
no,
exact.
our the ground floor any that
So
every seminar room is like this.
auditorium size.
Yeah, yeah, right. It's going towards the lower.
But the measurements that we used for everything was precise to that room at JU.
Okay.
Anyway, so to your point, yes, I mean the same protocols with the obvious changes, of course. But that's, here what they're doing is they're putting a person over here These are the ambient streamlines. There were three windows and one door. The windows serve as the inlet, the door as the outlet, and thus things are escaping from here. Uh, Now, this person is the teacher who is standing at the desk, and whatever that person is reading out is leading to the door. While this person is sitting at the front of the room, same thing. This person is in the middle of the room, one of the students, slightly higher up. This the particulates would be mixing like this to the room. And whoever is at the back benches, apart from messing up the class, can do a lot of bad things as well, as in spreading the pathogens more efficiently throughout the room. So yes, this can be done. But like we have some more. Yeah.
Example, in this the previous example, if we have a particle that is it stands at this, it gets attracted. Another particle hits on another surface, it gets attracted. There are chances that they both will interact with each other.
Yes,
So that is not captured.
that is not captured. So particle-particle interaction is not captured.
But what happens then? If
So
there is
you're
a
saying that it has deposited in on one of the one wall, and it has what it would do after interacting.
then is it group two particles after reflecting is in the airway, but they are touching kind of. But how that CFD will take care of it? Because we see in this we have
This our safety model won't take care of it. So that is beyond what we are doing. But in terms of what it can do is, I mean, the obvious things there could be like if you probably cannot think of it as point particle anymore. So you need to think about the deformations, whether there could be coalescence.
If it's very minor, micro-sized droplets, Gopal is already doing it. Right? Droplet coalescence, that kind of thing. So yeah, but like if they're interacting and they're like coalescing, then droplet coalescence model will be like if it is droplet, if it is like some deformable solid object and how they combine with each other, that is again that you have to look at the individual interaction. But droplet coalescence, like Chandas has group, they are doing it.
see this model. I think there is no
So
interaction. Even
instead
There,
of said that
there
yesterday
is no
also
interaction.
even if they are
chemically inert particles.
yeah,
Yeah.
even if they are touching, there is nothing is
Yeah.
happening.
We are assuming that the particle or the particle spatial distribution is sparse enough that any particle collision at that scale, for these are very tiny particles, right? So it does not have any overall effect on the dynamics that we want to extract. So I think in terms of the material that I have prepared for you guys, we are very close. I probably would have just one and a half hours at most of material left for tomorrow. Dr. Shamanta is going to do convert some
How
topics.
would I like if that software is not installed?
No, they can still do it. It is there. They have to start from the mesh stage. So the .msh file that is saved, you need to say, open it up, follow the protocol that's already there on the folder, and what I did since morning. Like what I did is agnostic to the version number, as long as you start from the .msh file. So you can still work on your own if you want to.
So one thing I like up one thing.